So just I'm going to start. Okay, good morning to all of you. So we'll just in the last class we have discussed regarding association rule mining, and we have actually done this a priori algorithm. Now, what the next is that since we have seen that to improve the efficiency of the a priori algorithm, because as we have seen that it is very good for a small data set, but when you increase the data size, then it becomes inefficient because of complexity involved. Because in that case, the number of input outputs requirement becomes more, and hence complexity increases significantly. So what we are doing right now is that there are variations like you can see that variations like hash based technique, and then uh, tra- transaction reduction, then partitioning, then sampling, and then there is dynamic item set counting there. So we'll be discussing few of them. Uh, the first which I'll be discussing is the sampling algorithm. Okay. So what we do in sampling algorithm is that we take random transaction of the original database and then placed in much smaller sample database. Okay, fine. So obviously, as far as sample size is concerned, it will be like that, so that it can actually reside in the main memory. So whatever be the main memory size, it should be less than or equal to the main memory size. Okay, fine. Uh, Obviously, this reduces the number of database scans to at most two, because when you go for one sample and that too is in like the size of the main memory, so with one go, the algorithm will execute. Okay, simply. So, what we do actually in this case is simply by just taking, like, you have data D, then out of this small sample SI we take, and then we are applying a priori. Okay, this SI should be equivalent to your RAM size. Why? Because your main memory size should be, or the sample size should be less than or equals to main memory size. Idea is very simple, that in one go the a priori algorithm should actually execute. So that is what the thing is. Now the question is that when you go for, then what we have is we call it as potentially large item sets. We call it as PL. Okay. This PL is actually what we are getting in case of normal a priori. Excuse me, I think all of you should mute yourself.
Sir, everyone is on mute.
Okay. Okay, fine. So what we have is actually when you apply, say this is my S1 sample one, when I am applying a priori. So in case of normal a priori, we were getting some L, large item sets. In this case, what we call it as PL, potentially large item sets. Okay, this is what we have. So applying a priori on the samples, you get PL. Now there is always the possibility that I'll be losing some of the item sets in this case, because the sample size compared to the entire data size is very small. So there is always possibility that I may lose some of the large item sets. So we have to do something to include such uh, large item sets which are actually missed by the samples. Certainly, we cannot do it in a, like in a 100% surety. But what we are doing it in a probabilistic manner. So for that, we have to implement this what we call it as negative border function. Okay, NB function. This NB function will actually compute some of the probable say a large atom sets which could be combined with PL. So that means I'll be looking for L where actually PL union NB will be. Okay. So negative order functions will have some sort of items. PL is having some set of items. Taking the union of this will have it. And obviously this negative order function will be generated by PL only. So just let us see that. So the algorithm is very simple. That sample transactions take sample transactions from database D, then using a priori algorithm find PL from the sample database, and then the candidate set C1 contains item sets from PL union NBPL. So it is a negative border function of PL. Okay. So how to generate this the negative border functions? So this is pseudocode. Let me tell you with example. That suppose you have this as item sets. Say ABCD are 4 item sets, which actually involved in transaction database. Now, out of this transaction database, you are taking some S1. So while taking S1 and applying a priori on this, you'll be getting this PL. Okay. What you got is A, C, D, and CD are actually the potentially large item sets in this case. Now, obviously, what we do is that uh, we are just trying to create to have this negative border functions computation right now. So what we do is that you can see that you have this, you have this, you have this, you have this. These 4 are the potentially large item sets. Now just remember that we have a priori property and anti-monotone property. So if you are using those two properties, you know that if A is frequent and C is frequent, then there is a high probability that AC will also be frequent. Okay. If A and D are frequent, then there is a probability that AD also will be frequent. I think rest this and this cannot be because actually the B is not frequent, so all these B combination will not be. So this in first case, negative order function will have AC. Okay, this will come. So now this PL becomes A, C, D, C, and AC and AD. So now we have 6 items instead of 4 items. So I'll move forward and then I'll be going for computing the next level negative order functions. So what will happen is that I'll be generating this like I'll be generating this ACD. Okay. The reason is that AC is also frequent, AD is also frequent, and CD is also frequent. All the subset of ACD are frequent. So now negative border function in this iteration will have ACD. Now others A, B, D, and B, C, D all are having B, and since B is not frequent, obviously this cannot be a part of the and negative order function. So now we have ACD. So all together you will be having now negative order function is having certainly I cannot go further because next iteration only ABCD will be there, where actually B is not a frequent item set. So we will stop here. Now negative border function is generating AC, AD, and ACD. So now I can generate L, which is nothing but PL union negative border function of P. So I am getting A, C, D, AC, AD, CD, and ACD. So this is your final uh, large item sets, you can say your frequency. And now certainly you can apply similarly what we have done in last PRE, that just you can investigate these for association rules. I can investigate for say a this or for this also, depending upon confidence. So this way, the sampling algorithm works. So what the steps are very simple. That first of all, take the sample out of the transition database. Sample size should be less than or equals to the RAM size, just because that actually enables you to execute the entire algorithm in one go. So that I can do. Uh, so one time reading of the database will be required in that case. So that is why I'm saying one more. And then whatever large item sets you are generating, we are calling it as potentially large item sets, that is PL. Now using PL, I'll be generating the negative border function of PL. So whatever items, the combination of items you are generating in NV will be added into the PL, and that becomes your L. So once you have L, then certainly you can go for association rules checking and based on confidence. So that we are doing it. Okay. Hope it is clear to all of you. Now next is partitioning. Partitioning is very simple. That what we are doing in this case is that entire D will be partitioned into n partition. Obviously, what we wish that each DI should be less than equals to your RAM size, because in that case what will happen is each the a priori can be executed for each of the DIs in one scan of the data. So that is what we do. Okay. So what we have is certainly we'll be having say a large item set for L1 will be for D1, then L2 will be for D2, then L3 will be for D3, and similarly Ln for Dn. So you will be having generating this L1, L2, L3, Ln. And now L becomes L1 union L2 union Ln. So this is what partitioning does. The thing is, in this case, certainly this again cannot assure you 100% that all the large item sets will be captured by this, because actually you are applying the algorithm on a small data samples instead of entire database. Though, but the beauty is of this partition algorithm that you are considering the entire data set and you are applying algorithm on entire data set in a partition manner. And then you can always check for association rules based on confidence. Okay. So this is a simple pseudo code for that. That you split database D into n partitions, then using Apriori algorithm find the large item set for each of the partitions. So let Li denote set of large items of partition I. So candidate set C will be generated by union of, that is, NLI. Okay. So scan the original database, check the minimum support for each transaction C in C. If the criteria is met, add C into L. Okay. So because this actually generates C, and now what you do is that you just go for one scan of the database check, where actually you are looking for support percentage to be applied. Support percentage is always, I think, can be applied on partition as well as the union of the all large item sets. That is what we do it. And this is just an example that we are actually you can do. So you can have L1, L2, L3 in this case, and L becomes L1 union L2 union L3. These are just whatever I have told you, that examples is cited out here. Okay? And rest confidence level will be used to have this. Okay. The next algorithm is hash-based algorithm, which is actually is again the variation of the a priori algorithm, and can be used for larger data set. So what we have is actually we actually use direct hashing and pruning technique, which we call it as DHP, uh, where actually efficient generation of FI is two item sets first generated, and then we make use of hash functions to generate the next level of candidate set in this case. Okay, so obviously it is actually involves efficient counting is there, and then there are some subset functions which will be used for finding all the candidates containing the transactions. So when a two item set is hashed to a bucket, the count of the bucket is incremented. Let me tell you with example. So this is what examples we have done in the last class. So this is my transaction data. Then we are applying support percentage, say 50%. So applying this support as 50%. So I'll be getting this. So what we have generated is L1. L1 is this 1, 2, 3, 5, ignoring the 4. So now when you go for candidate set C1, C2, sorry, then what you're doing is actually you are doing this self joining of the set. So by joining L1 with L1, we will be getting all combination of this. Now in normal API, what we do is that we check this for in the database itself for frequency, so support percentage. So hash based technique says that we can apply hash functions out here itself. Say like suppose this is what we have. So I'm using here that is hxy, where actually you can see that I'm applying this hash function, where actually this means that if I have 1 2, then this I can have 1 into 10 plus 2, it will be 12. So this function will look like this. Okay. Now what we are doing is simply, first of all, each of the transactions items will be paired individually. That means what I am doing is that individually these will be paired. So we have 1 3 4. So I'll be pairing like 1 3 1 4 and 1 3. Similarly, I'll be going for 2 3 2 5 and 2 3. So what we have done is this. Okay. So this is actually a this we got it after this pairing of the items. Now then we can map this to the bucket. See what we are doing is that since you can see that I took this as uh, I took this as mod of 7. So obviously I know that mod of 7 can generate 0 to 6 remainders. Okay, either it will generate 0, or if it is the number is divisible. If not, then it can generate maximum 0, 1 to 5 as remainder. So I have actually that is why the bucket number are actually numbered as 0 1 2 3 4 5 6. So we have 7 buckets in this case. So what we are doing is you can always pick this first item 1 3. 1 3 if I pick and I'll fix it, I'll just map it to my hash function. So it will 10 plus 3 is 13. 13 mod 7 will give you 6. So you can see that this 1 3 is actually put out here. Okay. Similarly 1 4, so 1 4 is 10 plus 4 is 14. So 14 mod 7 is 0. So 1 4 is we kept here. 3 4 is 34. So 34 is actually giving the 6, remainder 6. So I'll be getting this. So similarly you can see 2 5, so 25. 25 is mod 7 is actually 4. So it will be kept in 4. So all the pairs will be mapped to the hash function, and whatever will be the remainder, accordingly it will be allocated the bucket. So it will be on 0 1 2 3 4 5 6. Now next what we are doing is that you can see that this is 3, this is 1, this is 2 instead. 2 items are there. This is 3 pairs of items. This is 3 pairs of items. This is 1 item. Now support is your 50%. So I believe that since transaction is 4, so whatever is more than 2, greater than 2 instances will be considered. So we have considered this and then this, then this, then this. So depending upon this, and these are the numbers that there are three items are there. There are one items, two items, zero items, three items, one items, three items. Now what we are doing is that whatever bucket is having the minimum percent support count, then I am just allocating one. So I have allocated one to this, zero to this, one to this, zero to this, one to this, zero to this, one to this. So once you do this, so now I can allocate this all, like we have self join L1 L2. I can assign the value to this 1 3 1 2 3 3. So accordingly to the bucket count I'll be assigning. So I'll just ignore this, I'll ignore this, and then I'll be getting 1 3 2 3 2 5 and 3 5. So that is this. Okay. So this becomes my seat. So this way, like we have generated C2 without referring the data, just to have a hash functions using it on this, like this way. So this becomes C2, and certainly the frequency is high, so that becomes your L2 also. And then certainly if you are interested, then you can go for next level also. Certainly the hash function will change in the next level also. So that way we apply hash-based algorithm to have it. The efficiency will improve in the sense that in multiple iterations the data scan is not required. So that we do it. Okay, fine. There is another thing which we'll have to see, that what is transaction reduction, by the way. Let me tell you what is transaction reduction. Okay, the see what is happening in this case, that whenever whenever I calculate this support 50%, the number of transaction always matters. Since number of transaction is 4, then always we wish that greater than 2 or equal to 2 will actually generate this percentage. So item or pair of the item or any combination of the item having the occurrence 2 or more will actually tell you the percentage of the support. Okay. So it says that there is a possibility that suppose I have 500, there is a transaction, and say it is only 4 is there. Okay. Or obviously the moment I say only 4, now the number of transaction becomes 5. So in this case, all the percentage 50% always be achieved either by 3 or more. Okay? Either by 3 or more. So uh, in that case, what will happen is that you can see that these two and this becomes your frequent item sets, whereas this becomes 2 and this becomes infrequent and this becomes okay. This is what we, by modifying, just having one transactions in this, I'm having such. Okay. So what we are doing is that now just investigate the transaction again. Okay. Now what is happening is the one is in transaction 100 and one is in transaction 300. But in case of one, there is 3, 4, 2, 3, 5 also, and these are frequent items. Okay. Now, but when you go for this particular transaction 500, what you found is that only the transaction is having the occurrence of 4 only, and 4 becomes infrequent. Okay, so the moment 4 becomes infrequent, then this particular transaction has no role in the association rule binding. So what it says is that when you move to generating your C2, like suppose uh, when you generate C2, what happens actually in this case is that again in C2, just when you go for investigate 1 3 or 1 5, say once you go for this, certainly this will not be there. So I'm just going for 2 3. So I'm investigating these numbers, how many times this is appears. So it says that this actually transaction, presence of this transaction will actually create problem, or which actually is an inefficient way of considering this. So what it says is that when you move to the next step, what you do is that don't consider this. That means ignore this while calculating the support percentage. So what will happen in that case? That in the first iteration, my support percentage is calculated on the basis of 5 transactions. Whereas since 4 becomes infrequent, I'll be ignoring this transaction. So in next C2, the whatever combination of items frequency is actually you can say investigated, will be investigated only for the 4 transactions. So all the percentage of support percentage will be calculated based on the 4 transaction only. So what will happen is anything is 2 and more than 2 will be considered. So in the first iteration, uh, 3 or more is considered, whereas in the next iteration, by ignoring 1 transaction, I'll be considering 2 and more also. So that efficiency comes in between when you have transaction reduction. Certainly, it will be very helpful when you are talking about a large data items or large transactions. Say if you have a 1 lakh of transaction, and suppose you actually land up in a case where actually 10,000 transaction becomes you can say irrelevant in terms of frequencies, then if you reduce the 10,000 transaction out of 1 lakh, then certainly the support percentage will be calculated on 90,000 instead of 1 lakh, and that will actually have a very good impact on the pattern generations, because it make in that case you may not lose some of the significant pattern out of it. Okay, that is what we do it. Now, so all the variations are actually we have covered the variations. Now, what we are doing going for it is that there is a multi-level association rules. Just I think I have told you in the very first class. So you can see that you have a food, then you have a milk and bread. Milk might have two different, say skimmed milk or 2% sort of milk. Or bread be I'll be having wheat bread and white bread. Then again 2% milk will be having some flavor sunset. This example is taken from, I think probably some example from some foreign country. So that country is having some sort of these. Now what we are saying is that milk and bread, I'm saying that my support is 20% and confidence is 60%. But the moment I go like I'll be going for this 2% milk with wheat bread. So what we are doing that either you can be with this, or what we are doing is that I am reducing the support and confidence in this way, 6% and 50%. So 20% becomes 6% and 60% becomes. If you are going down the level for the session rules, if you are actually reducing the support and confidence, then it is a reduced support we call it. Whereas these are known as that you are having multi-level of association rules. That means not only milk with bread I am considering lower level like skim with wheat bread, skim with white bread, or 2% with white bread and 2% with wheat bread also. And you can go down as well. And either it is up to you that you want to actually reduce the support and confidence percentage, or you will be strict with the same one. So in one case, it will be referred as uniform support and confidence. In another case, it will be referred as reduced support and confidence. This is the case of reduced confidence and support percentage. Okay, so that is what we do it. So always when you have support, uniform support and reduced support, certainly in case of uniform support, I told you that same minimum support for all levels will be used. So one minimum support threshold will be there, and that will certainly, if too high, means low level associations. If it is too low, it may generate too many high level associations. So depending upon your requirement, you can go for it. Whereas actually reduce support is actually that you can reduce the support and confidence in the lower levels. Actually, that will actually give you a good results. Okay, fine. So I'm just leaving all others. This is not for your use. So I'm just, so a priori we have completed. Now I am going to share the another one. Uh, Next is there is another algorithm which is known, very famous algorithm is known as a frequent pattern approach. Okay, the uh, the thing is it actually overcomes the problem which we have witnessed in the a priori. So what we are doing in a priori is that we are generating the candidates. Candidates means like when will be like say, when we say that when we have like you can say that say C1, C2. So what we have is actually in case of a priori we are generating this. What it says is that in case of FP growth there is no need to generate any candidates. So obviously this has a very good impact on the algorithm and also on the pattern also. So the method is very much divide and conquer methodology. That means you will be decomposing the mining task into smaller ones. Okay, fine. It requires only two scans of the transactions. In the first phase algorithm, I'll be constructing the frequent pattern tree, whereas in second phase, I'll be constructing the, I'll be just investigating the FP tree and I'll be generating you can say association rules for out of it. Okay, that is what. So only requires two transaction database scans in the first phase itself. In second phase, there is no requirement of any scans. So that is what we do it. Okay. So these are the things which is involved in FP tree constructions. So we have item prefix tree, FI header table, then dependent on ordering of items, we'll be sorting the items into decreasing order, and the niche transaction is viewed as a list of FIs in descending order of support count. So just remember that I'll be using this. So just see that. Just concentrate on this first. Okay. This is my transition database. Okay, fine. It is very easy. Don't be panic. I'll just tell you that it will be very easy right now itself. So this is my transaction. These are the items. Okay, what I'm doing is I'm just looking for frequencies and I'm fixing the support as 0 0.5. Now you have 5 transactions, so obviously greater than equals to 3 number of transactions will be the 50% support. So what we have is we have checked this, and what we got is that F, C, A, B, M, P, these are having the frequency which is 50%. So we have selected these. Now what you do is ignoring the infrequent items out of this, selecting all frequent item sets and make the order from say from decreasing order in decreasing order. So what we are doing is that I have fixed F, C, A, M, P in case of decreasing order of this frequency of the items. Now, your question might be that, sir, F and C are same. So obviously, you can keep F or C anyone as one first item. But remember, once you fix C as first item, it will be in all cases it will always appear before F. If it is F first item, then it will always appear before C. Now, now you can see that A, B, M, P is also having 333. So sequence you can fix anyone. You can take anyone as first, second, third, fourth. But only the thing is whatever you have selected in the first case, it will be actually followed in the all the cases. Just remember that. Otherwise, there is no problem. So we have actually the frequent item sets which is ordered in decreasing order manner. So this and this and this. So transaction wise you have to do. What you have to do is this is the transaction. These are the items going for the first level of frequencies having minimum support as 50%. Then ignoring the infrequent items, make the order of the items and keep into this way. So we have this. So this we got it. This is the first two steps. Now the next step is how to create this particular. This is my tree, what I am having. Okay. Now, now let me tell you that how this tree is actually generated. See this. I am just taking this as root of the tree. Then what I am saying is that you have F, then C, then A, then M, then P. So I have used the first transaction and I have created this F, C, A, M, P. Now I'll be going for next one, that is F, C, A, B, M. So I'll not go for the next branch, rather than I'll just traverse from this branch itself. So I'll say F, so I'll say F becomes 2 in this case, because the first instance, now the second instance. Now this is becomes 2, A becomes 2. Now after A, there is B. Okay. Whereas in this case, first M, then P. So obviously it will not go in this branch. What I'll do is that I'll create another branch B and M. Okay. So I'll say 1, I'll say 1. And this is my 1. This is first initial case. So this is my second transaction is done. Now the next is FB. So certainly I can say that this becomes 3. B cannot, this is C, so what I'll do that I'll create another branch B. So this I have to create. The third is CBP. I cannot traverse in this because the first element is F. So what I'll do is that I'll create another branch C, B and P. This is 1, this is 1, this is 1. Now the next is FCAMP. So obviously what I'll do is that FCAMP again. So what I'll do is that I'll cut this 3, it becomes 4, this becomes 3, this becomes 3, this becomes 2, and this becomes 2. So this is what you got. So all the transactions I have considered. Now you can see that the same tree this is having, where actually you can see the F4, C3, A3, M2, P2, then B1, M1, then B1, C1, B1, and P1. So this is why I got it. So this is my tree which I got it from this transaction database. So this is my frequent item tree. Now I just need to, so this is where actually a transaction use is over. Now just I'll traverse this tree and I'll get my association rules. This is very, very easy. Okay. So what you have is this. So what you have is you can see that F4 and C is 3. So that means FC altogether has the occurrence 3 at least in this case. So if I'll go for this particular branch, then F and C is appearing 3 times together, because that is why. Now I can also figure out that CA is also FCA is also having three frequencies. Even I can FCA is having three. This I have. This MP is two. So depending upon that what confidence you are looking for, these uh, association rules can be checked. So what I can check, since this is F F C A is say 3, so I can say that okay, I'll be checking for this CA and CA as F, or FC as A, like this. So all such will be checked. So that you check with the confidence percentage, and then you get the association rules. It is very easy and very effective also. So this is very famous also in very various applications apart from all decision type of algorithm. Even it is very much useful in financial data also. Okay. So these are the steps which we have. So what we do is that we construct the conditional pattern base for each node in the tree. The conditional pattern base is actually talking about these things. Let me tell you, if I say this is my conditional base pattern. What I do is that you can see that C, from C you can go, like you can traverse F three times. You can see that from C, you can traverse F three times. From A, you can traverse FC three times. From B, you can traverse FCA one times, F one times, C one times. From M, I can go like this. From P, I can go like this. All these conditional pattern base is actually coming from this. That I can see that M. So here is M, and where is there any? Here is M. So there are two M is there. So I can see that from M, this is 2. So that means I can traverse FCA twice to reach this M. So that is what I am writing. FCA twice I can go. For this M, I can traverse FCAB. So I can go for only one because this is one only. So this is conditional pair. If I go for this B, then there is here is B, here is B, and here is B. So you can see that since the index is 1, so I can traverse FCA 1 times. So I am having FCA 1 times. For another one, I can go for F 1 times. So F C 1 times, so C 1 times. Now, certainly I can go for what is that? This actually gives that FCA altogether is 3 times occurrence in the transaction. So obviously the confidence will be high in this case. So I can check that. Okay, altogether. So with the confidence checking, I can generate the association rules. That is what we are doing in this case. So this is what we are doing. Obviously, these such you can see that out of this I can have this. So these can be checked for association rules. Same conditional part will be there. So this is what we have, and obviously there are some like properties are there, like you can see that the properties like pattern growth properties, it says that let alpha be a frequent item set in DB, B be the alpha's conditional pattern base, and beta be an item set in B, then alpha union beta is a frequent item set in DB if and only if beta is frequent in B. That is what we have. So for example, A, B, C, D, E, F is a frequent pattern if and only if A, B, C, D, E is a frequent pattern and F is frequent in the set of transition containing A, B, C, D. So this is something that this is something as what I am saying, that if F I am saying AC is 3, sorry, if I am writing say C, if I write F A is 3, that means I am talking about FAC or FCA, whatever is there, as 3. So this is what we are talking about. Okay. So that way you can generate. So why is FP growth fast? The simple is the FP growth is an order of magnitude faster than a priori. And the reasoning is that no candidate generation, no candidate test is required in this case. It uses a very simple data structure, a tree data structure. And obviously it eliminates the repeated database scan which we require in the a priori. So basic operation is simple, counting and arbitrament. So that is why this is important. Okay. So this is one thing which uh, you can have. Okay. So I think we have covered today the variations and happy growth, both the algorithm. I think these sets of algorithms are actually used for associative mining. Depending upon your requirement and the data, you can use any of these algorithms. Okay. Rest in the next class, I'll be just giving you some observations on a priori, on association rules, and then I'll move to the classification part. So I'm just stopping out here for today's class. Okay.
Okay, sir.
Okay,
Sir,
because
next class, when will you be taking?
uh, uh, next class I'll take any